What specific problem does the length-controlled policy optimization (LCPO) method aim to solve in the context of reasoning language models?
The length-controlled policy optimization (LCPO) method aims to address the uncontrolled length of reasoning sequences generated by language models, which leads to inefficient compute usage and suboptimal performance. Specifically, LCPO provides precise and adaptive length control by training models to meet user-specified length constraints while ensuring the correctness of the final output. This is achieved through a reinforcement learning framework that couples accuracy with output length, allowing models to generate reasoning sequences that either match an exact target length or do not exceed a maximum length. By overcoming the limitations of previous methods, such as the rigid strategies employed by S1, LCPO enables models to dynamically allocate inference compute based on task-specific requirements, thus enhancing both efficiency and reasoning performance. Ultimately, LCPO allows for a more effective trade-off between token budget and reasoning accuracy across various tasks.
How does the proposed method LCPO work? Please illustrate its operation step by step, including the reinforcement learning objectives and reward function used.
The proposed length-controlled policy optimization (LCPO) method operates in a structured manner to enable reasoning language models to generate outputs that adhere to user-specified length constraints. First, it begins with a pre-trained reasoning model and augments the input prompts by appending a target length instruction, creating a new dataset that includes both the prompt and the desired output length. Next, LCPO employs a reinforcement learning (RL) framework, specifically using the GRPO algorithm to update the model based on a dual objective reward function. This reward function consists of a correctness reward, which incentivizes the model to produce accurate answers, and a length penalty that encourages adherence to the specified target length. The balancing parameter, alpha, regulates the trade-off between these two objectives, allowing the model to prioritize correctness or length compliance as needed. Finally, during inference, the model generates outputs by selecting a fixed target length, ensuring that the reasoning process aligns with the specified constraints while optimizing performance.
Can you provide a simple yet illustrative example of how LCPO alters the reasoning process compared to traditional methods? Walk us through an example to clarify this.
An illustrative example of how length-controlled policy optimization (LCPO) alters the reasoning process compared to traditional methods can be seen in the way it handles output length constraints. For instance, consider a math problem where the model is prompted to generate reasoning for a solution with a target length of 1024 tokens. Traditional methods like S1 might truncate the reasoning mid-process if it exceeds the token limit or insert a special token to continue, which can disrupt the logical flow and lead to inaccuracies. In contrast, LCPO allows the model to adaptively generate reasoning that fits within the specified length while maintaining coherence and correctness. For example, with LCPO, the model can produce a complete reasoning chain that effectively utilizes the 1024 tokens, ensuring that the output is both accurate and adheres to the length constraint, thus avoiding abrupt truncation and enhancing interpretability. This results in a more efficient reasoning process, as demonstrated by L1 outperforming S1 by significant margins in terms of performance and adherence to length constraints.
What are the key theoretical or practical benefits of using LCPO compared to previous methods such as S1 and other length control strategies?
The key theoretical and practical benefits of using length-controlled policy optimization (LCPO) compared to previous methods like S1 and other length control strategies include its ability to provide precise and adaptive length control for reasoning language models. Unlike S1, which relies on rigid hand-engineered strategies that can disrupt reasoning by truncating outputs mid-sequence, LCPO intelligently adapts the reasoning process to fit within specified length constraints without sacrificing accuracy. LCPO trains models to optimize both correctness and adherence to user-specified length constraints, resulting in significant performance improvements, up to 100% relative and 20% absolute gains on math reasoning tasks compared to S1. Additionally, LCPO trained models demonstrate strong generalization capabilities to out-of-distribution tasks, maintaining high performance across various benchmarks while effectively managing token budgets. This flexibility allows for a more efficient allocation of computational resources, making LCPO a superior choice for length control and reasoning tasks.
How was the effectiveness of the LCPO method validated in the paper? Discuss the experimental design, datasets, and metrics used to benchmark its performance.
The effectiveness of the length-controlled policy optimization (LCPO) method is validated through a comprehensive experimental design that includes training and evaluating the L1 models on various reasoning tasks. The experiments utilize the DeepScale R-Preview dataset, which consists of 40,000 question-answer pairs from mathematics competitions, and evaluate the models on test sets from 4 different reasoning datasets: AMY 2025, Math, AMC, and Olympiad Bench, as well as general knowledge benchmarks like GPQA, LSAT, and MMLU. Performance is benchmarked using 2 primary metrics: the mean deviation between the generated token length and the target length, and the overall problem-solving accuracy at different target lengths, 512, 1024, 2048, and 3600 tokens. The results demonstrate that L1 models significantly outperform the S1 baseline and maintain precise length control, achieving up to 100% relative and 20% absolute performance gains on math reasoning tasks. Additionally, the L1 models exhibit strong generalization capabilities to out-of-distribution tasks, further validating the robustness of the LCPO method.
What significant results did the authors achieve with their new method, and how do these results compare with existing models? Be specific about the performance improvements noted in the paper.
The authors achieved significant performance improvements with their length-controlled policy optimization (LCPO) method, particularly with the L1 models. Specifically, L1 outperformed the S1 method by up to 100% relative and 20% absolute on math reasoning tasks under identical conditions. Additionally, L1 demonstrated superior performance across all token budgets while maintaining precise length control, achieving over 100 to 150% relative and 20 to 25% absolute performance gains compared to S1 at 512 and 1024 token budgets. Remarkably, L1 also matched or surpassed the performance of the original base model, AGENTICA4K, while using fewer tokens, and it was the first instance where a 1.5B model outperformed larger models like GPT-4o at the same token budget. Overall, these results highlight L1's ability to adaptively optimize reasoning performance while adhering to user-specified length constraints, setting a new benchmark in the field.